This is Geology 100 Natural Disasters. My name is Dr. Scott Nowicki, and today's topic is the impacts of climate change. Thanks to ice cores that we've drilled in Antarctica and in Greenland, we have a very good record of the climate over the past few 100,000 years. We know how much CO2 and methane and other gases have been in the atmosphere during that period of time. We know approximately how warm or how cool it has been from year to year over the past few 100,000 years. We have some sense in how much particulate matter was in the atmosphere from, let's say, volcanic eruptions or other big events. So this record of information tells us that certainly there are cycles to the climate. But at the same time, right now, what we're observing is an unprecedented change to this global climate. For the past 650,000 years, the amount of CO2 in the atmosphere has ranged between about 180 and maybe 300 parts per million. And now we are looking at approaching 400 parts per million. And as we look into the future, it looks like it's going to go higher and higher, effectively a function of human influence on our environment. So the big question is, of course, where is the CO2 coming from, and can we potentially do something about it? This entire story about where CO2 came from originally, is going to, and is getting back into the environment, is all about plants. Now, early in geologic history, if we go back billions of years, CO2 was pretty abundant in the atmosphere. There was a lot of initial outgassing of CO2 as a function of volcanic eruptions and early planetary formation. But then starting about 2.5 billion years ago, that carbon dioxide was consumed and started to get replaced by oxygen. And then ever since then, CO2 has been decreasing in the atmosphere, and especially over the past 500 million years. So here we have a plot showing the past effectively 540 million years worth of history. And here is that atmospheric CO2 line, and you can see that from early Paleozoic into late Paleozoic, and then there was a bump up in the Mesozoic, and then it continues to decrease as it gets closer and closer to today. CO2 has been dropping drastically. And at the same time, global temperatures kind of go up and down as a function of the changes in the amount of CO2. The reason why this overall trend is occurring is because plants are on the surface, and plants do this amazing thing. They pull CO2 out of the atmosphere, and that generates energy that then they store as biomass. So in comes sunlight, carbon dioxide, and water. Thanks to photosynthesis, out comes oxygen and effectively glucose, these carbohydrates that plants produce. Photosynthesis is the number one means by which CO2 is being pulled out of the atmosphere and turned into something else, turned into solid, or in most cases, green plant material. Thus, photosynthesis produces these carbohydrates and oxygen. Turns out this isn't the only method by which the Earth absorbs CO2 and turns it into a solid. The oceans are actually absorbing CO2 out of the atmosphere, and as that CO2 gets consumed in different ways, it actually turns into sediments, limestone that accumulates at the bottom of the ocean. But in the short time scale, we're really talking about plants. The origin of CO2 is relatively simple. It comes out of magma. That's why we had a bunch of CO2 on the planet to start with. But now if we're looking for sources of CO2, it of course comes out of animals. As plants produce apples, we take the apple and we eat it, and we take that energy that was stored as chemical energy and we break it back apart and we turn it into mechanical energy. That process of digestion re-releases the CO2 back to the atmosphere. Now, CO2 is also produced by decaying plant matter. You look at a single plant, a tree, it is this effectively storehouse of carbon dioxide. And then as those plants die, they then re-release the CO2 to the atmosphere. This, for the most part, is what we refer to as the carbon cycle. This carbon dioxide is released in the atmosphere, plants pull it in, they grow, they die, and they re-release the CO2. Animals consume those plants, they die, they release the CO2. So it's this constant cycle of production and sequestering of CO2 into biological material. There are a number of environments where this occurs, really all over the planet. Plants are doing this. They'll do it in wetlands when there's abundance of water and all sorts of nutrients, so that as plants grow out of the water, they absorb CO2 out of the atmosphere. And then fairly often when they die, those plants will then fall into the water in this anoxic environment and actually not break down for a long period of time. This of course occurs on land. We can see grasses and shrubs and trees that grow almost all over the planet except for in the driest of environments. And then this also occurs in the ocean, where algae and seaweed and abundance of photosynthetic organisms can grow within the water column. Then when they die, of course, they sink down to the bottom, or they break back down and turn into carbon dioxide within the water column. Now this is an image off the coast of Ireland that actually shows an algal bloom, meaning a higher than normal level of photosynthetic organisms in the water. All this photosynthesis occurring is actually sucking all the CO2 out of the water and making it difficult for plants to survive. So these algal blooms will occur and create these dead zones in the water shortly thereafter. Now in certain environments, these plants are easily deposited in accumulating sediments. They are buried, compacted, and heated. Plant material, these carbohydrates, these lignins, the cellulose, turns into these hydrocarbons, these higher density energy molecules. It is removed from the surface of the earth and fairly often stored for geologic periods of time. Those swamps and wetlands, when those plants fall into the water and accumulate, they get compacted and heated, that turns into coal. So the coal that we're mining out of the ground was this ancient wetland environment. This algae in the ocean accumulates in these layers and cooks for some period of time and then becomes oil, which can flow underground. It can flow through rocks or flow through fractures and actually work its way to the surface. This is an image of a tar pit where this oil is actually making its way to the surface, kind of like a spring of water would reach the surface. Where oil accumulates and is trapped, that's where these locations are that oil companies currently go and drill into the subsurface to tap into that reservoir of oil. So we find ways to obtain these different hydrocarbons that have been sequestered away in the subsurface in geologic environments. When we look at how much energy is stored within these hydrocarbons, the numbers are absolutely amazing. The average US gallon of gasoline requires approximately 90 metric tons of ancient plant matter as precursor material. That means for a gallon of gas, you need 90 metric tons of wood, or of leaves, or of other organic material. The fossil fuels burned in 1997 were created from organic matter that contains greater than 400 times the net primary productivity of the planet's current biota. That means in a single year, we are using more than 400 times the total amount of biomass that accumulates all over the planet in that same given year. This means that we are adding millions of years worth of stored carbon back to the atmosphere in a blink of an eye. These are these geologically sequestered, geologically separated from the environment sources of carbon that we are re-releasing back into the environment in a very short period of time in a highly effective manner. What we see for the past 400, 500,000 years has been the natural cycles of the carbon cycle. It goes up and it goes down as temperatures increase and temperatures decrease, as glaciers expand and glaciers retreat. We are seeing that cycle occurring. And then what we've seen recently, just in the past few decades, this ramping up of CO2 into the atmosphere is entirely a function of producing CO2 that is resulting from burning coal and oil and natural gas. Now, the record in the ice shows that the climate has been very stable for the past 8,000 years. CO2 and temperature go hand in hand. For the past 100 years or so, CO2 has been increasing more quickly than ever before in the history of the Earth. We are seeing this unprecedented change to CO2 that is driving this unprecedented temperature change. And there's corroborating evidence if we look in other places. First of all, we've been measuring real time what the CO2 concentrations in the atmosphere have been since 1958. Researcher David Keeling in the Scripps Oceanic Institute on Mauna Loa installed a CO2 sensor and actually started measuring the amount of CO2 in the atmosphere. And Mauna Loa is a pretty good place because there are winds coming in from different directions. It's a well-mixed atmosphere at that location. But over time, we can see that this number has been increasing. Now, if we zoom in a bit, we can see that this red line is actually the kind of monthly changes, so that you can see that from season to season it goes up and it goes down. Or as those numbers keep going up and down, there's this general trend of increase. So that back in 2005, we were at 378 parts per million. As that CO2 keeps increasing, we're seeing this resulting change within the environment. Just like in the climate record, there's this relationship between CO2 and temperature. Here is our source looking since late 1950s until today. As the CO2 has been going up, the temperature has been going up. With 1,000 years of CO2 and temperature observations, it's a pretty direct correlation that as emissions have ramped up in the recent 150 years, and even more extremely in the past few decades, the CO2 concentrations in the atmosphere have ramped up drastically, and the result to the environment is that the temperature has been ramping up as well. So as we project into the future, it looks like we're going to keep increasing the amount of CO2 in the atmosphere. We can only assume that the temperature is going to increase. Now, CO2 isn't the only gas that has been causing problems. It turns out that there are other radiative forcing gases, such as methane and nitrous oxide, and these are all following the same trend. As more agriculture occurs and more garbage goes into landfills, we're producing more methane. There's a lot of information suggesting that it's not just CO2, it's actually multiple sources that are causing these problems. So the results to the environment are, of course, the global mean temperature has been increasing. Here's our plot showing the last 150 years worth of global mean temperature. We can see that it has been ramping up fairly drastically as of late, but at the same time, the global average sea level has been increasing, and the northern hemisphere snow cover has been decreasing. All of these things, temperature, sea level, and snow cover, all correlate and are directly related to that CO2 in the atmosphere. What we're really interested is the temperature change that has occurred on the planet. Now, in order to actually see the temperature change, we've got to normalize it. So this is a typical global view of how warm the atmosphere is. Long wave flux in watts per square meter. What this really is mapping is how much thermal energy is being radiated by the atmosphere and surface around the globe. And of course, the highest temperatures are occurring close to the equator because that is the part of the planet that sees the most sunlight throughout the year. Take one of these maps on a yearly basis, let's say 2013, and subtract it from a previous temperature. So what we have are these temperature anomaly maps when you do that. Here is the year of 2006 minus this average that has occurred over a longer period of time. And the big thing that we notice here is that there are a lot of places around the world where the temperature has been increasing, that is higher in 2006 than it was in 1960. But there are also some places where the temperature looks a little bit lower. Temperatures have not increased evenly around the globe. The equator is not the place where it has gotten the hottest. The locations around the globe where it has heated up the most are these high latitude areas. These are the locations where originally there was sea ice and it was covering the surface of the ocean. As that sea ice melted, it exposes this warmer ocean, so it heats up part of the planet. The same thing is occurring in Greenland or in northern Canada, whereas snow cover decreases, then more and more ground is exposed to the sun and heats up as well. Now, mapping this out is pretty useful, but what we really need to do is generate models that can help explain exactly what is going on. So models are the key to understanding the causes of climate change, and we know that there are many factors. There's orbital dynamics, there are geologic changes, there's changes to the biology and ecosystems, and then there are these anthropogenic changes as well. And we have to take all of them into account in order for these models to actually tell us what we want them to know. The results of these models are very good for the past. We can build models that explain what happened in the past, and then as we look into the future, we can attempt to apply them. Now, they're not as good for in the future because we don't actually know what the atmospheric concentrations are going to be as we project 10, 20, 50 years out.